welcome everybody. Happy Easter. He is risen.
He is risen indeed.
Thank you. Absolutely. Absolutely. And that's wonderful, wonderful news. One of the things that oftentimes does get overlooked, in all the chapels we do, we always talk about Jesus being crucified and how he took all our sins upon himself. But a lot of times we don't realize that, if he wasn't raised from the dead, then Christianity really is nothing. So Easter is really the celebration. The fact that he rose from the dead and the fact that we're united to him through baptism and through our forgiveness means that we're going to be living together with him forever once we're finished with this world. So rejoice and be grateful. It's a wonderful time. So a little bit of housekeeping before we jump into our new section today, which is going to be momentum. What did the clock do when it was hungry? I like that answer better than the one I have.
He ate 9.
Nice.
Was that good?
I like that answer. It went back 4 seconds.
Oh.
It went back 4 seconds. Do you guys get that one? Because I actually don't. I was hoping you would.
He's like,
We went back for seconds.
Oh, man. Jocelyn got it too, I think. You got it right away. I saw that and I thought, why 4 seconds? You're still going to be hungry. So, okay. Good one. It is Monday, isn't
you have
it?
to like enunciate the 4.
Yeah.
4 seconds.
What do vegetarian zombies eat? What do vegetarian zombies eat? Grains.
Oh, grains.
We're off to a blazing start. So you'll notice the absence of a question up here. The reason for that is because we're actually finished with questions. So I'm going to give you right now the first and the last question for the AP Physics semester final, which will be in about a month, or not AP, regular physics, sorry. You can take the AP one too if you want. So the first question on your final is the one where it says you're driving with your cruise control set to 65. Your friend is driving at 95 and is passing you. How do your speeds compare when your cars are exactly next to each other? So that's the very first multiple choice question on the semester 2 final. Of course, the last one will be the last question that you guys got a little while ago. You and your friend are standing on a ledge at a quarry looking down at the water. You jump off. Your friend takes the frictionless slide. Who reaches the water first? And who is traveling faster when they hit the water? So those are the two questions, the first and the last. Anything in between is fair game for that multiple choice test. So be ready when that happens. And again, just like all this other stuff, if you're a senior, if you've got a cumulative GPA of 3 or higher, and if you've got an A- or better in the class, then you are exempt from that. So yeah, it's a kind of a standard policy for all the classes. So, thank you. Where are we going from here? We are going into the chapter on momentum. So loosen up your hands. We're going to take some notes today. You can title your notes Momentum. I don't think so. I think you're exempt from that whole day, right? Or from that class.
Oh, yeah.
Yeah, so you wouldn't have to be here if you meet those requirements.
Great.
So this chapter is actually pretty straightforward. The only things that might get a little difficult here is really the fact that we're going to be jumping back into some old stuff every once in a while. And if you didn't like the old stuff, of course, maybe it doesn't come back as well as you'd hope, but momentum is a pretty straightforward thing. I mentioned before that a lot of times in science, we think of terms like energy, and they're really nothing like what you envision them to be in the real world. Same thing with work. You don't think of work as being force times distance when you're asked to go to work or something. Momentum is the opposite. When we think of momentum, you think of like a big mass moving really fast. That's going to have a lot of momentum. But if you have a small mass moving slowly, that's not going to have a lot of momentum. And that's absolutely true. Because momentum is abbreviated with lowercase p, they just kind of ran out of letters. Capital P would be power. Momentum is simply equal to an object's mass times its velocity. So the bigger the object is, the faster it's moving, the more momentum it's going to have. So that should actually make some sense from a real-world perspective for a change, which is nice. Now, of course, the units on momentum are just going to be whatever units this is times whatever units that is. So mass is in kilograms, velocity is meters per second, and this actually is the unit on momentum, kilogram meters per second. We don't have a fancy word for this like, Newton or something like that. It's just kilogram meters per second. I think we should call it the Hathaway, but whatever.
Wait, that's the unit you said?
Yeah, this is the unit on momentum. So it's not one letter, it's actually kilograms times meters per second.
This was unit.
Yep. So these are your units on momentum. I don't think it's on the formula sheet, but it would be on the sheet where it says, what all the letters mean. I think it's titled formula letters or something.
But I'm asking if we're allowed to write that, or is that like...
You can write that, that's fine. If you forget, remember, mass is just kilograms, velocity is meters per second, so you're just multiplying those two. That's where it comes from. So you can find momentum just by multiplying those two things together. Very straightforward. And it's not just momentum where this comes into play. You can actually find change in momentum, which is something we're going to be doing pretty often in this chapter. Of course, change in momentum is going to be mass times final velocity minus mass times original velocity. And there's actually another term for this, which I will get to shortly. Another way you can find your change in momentum, these are all on your formula sheet, but it's good to write it down because it puts it in your head a little bit stronger. So change in momentum is also equal to force times time. If you're given a force and you know how long that force has been applied, then you can find your change in momentum that way. Now I mentioned there's another word for change in momentum, and that is simply impulse. So if you're looking for your change in momentum, what you're looking for is your impulse. That's simply what that word means. They're one and the same. Now, I mentioned before that we're going to be looking back at some stuff from a couple other sections, and I'm just going to point out what the important parts of that are going to be. Remember on your formula sheet that motion box, which we've been spending a lot of time looking at, both in that chapter and outside of that chapter. This is no different. There are really three or four equations that I want you to keep in mind from that motion box. And I'm going to put them on the board for you right now. So that's one of the equations, that long y equation, that's an important one. Got one of our velocity equations, that's an important one. Another velocity equation. And these are really the three main ones. The other one you should keep in mind is just F equals ma in general. And that'll help you out a couple times too. And we'll see how this all ties together. Just got about 2 examples and then that'll be all. Yeah, you'll be getting a worksheet. Okay. So, let's go ahead and take a look at a couple examples. The momentum box on your sheet is on the same side as the motion box. It's just off to the right of it. Motion is there. Momentum is there. How many of you guys played kickball when you were younger? Oh, good. That's kind of the classic grade school game, isn't it, outside? So here's our scenario. The kickball is pitched to the person, and it's going to the left at 5 meters per second because left is typically our negative direction. The original velocity is going to be -5, has a mass of 0.5 kilograms, and then this person gives it a good whack. So that's kind of your impact thing there. So when this person kicks that ball, we know that it takes 0.1 second for the ball to come off the person's foot, so it's just in contact for a very short period of time, as you'd imagine. And we'll say that he or she exerts 500 newtons of force on that impact. So the question might be, what is the change in momentum that this ball is going to undergo? In other words, I'm looking for the impulse, because impulse and change in momentum mean the same thing. So if that's something I want to solve for, remember that your change in momentum or your impulse is simply equal to force times time. And you've got force, 500 newtons. You've got a time of 0.1 seconds. So you can just multiply those two values together. And out pops your impulse. It's going to be equal to 50 And, you can see here the units would be Newton seconds. When you take into account everything that a Newton is, it would come to the exact same units as momentum, which would just be kilogram meters per second. So it's probably best just to keep this for all of your momentum units and impulse so that you don't get confused. But if you left it as 50 Newton seconds, you would not be wrong. So 50 is the answer. And what I'd like us to do right now is to try and come up with this answer in a different way. And this is what I'm going to give you a little bit of time to do here. So this is one way to calculate change in momentum here, but there is another way. You could just do mv minus mv original. You have the mass, you have the original velocity, you have this mass. So if you can somehow figure out this final velocity, then you can get your change in momentum using this method. And that's what I'd like to give you guys a couple of minutes to try and figure out on your own. These equations will help you. You don't need to use all the equations, but you can probably guess you'll need one of the velocity equations. So see if you can solve for your final velocity, and then use that velocity to figure out your change in momentum. And hopefully you get an answer that ends up being equal to 50. So go ahead, take some time. Another 60 seconds or so. Alrighty, I saw a couple people who had the right ideas in mind. Some people got all the way to the answer. Some people got really, really close, and that's good. So let's take a look at this one and see if we can confirm that the impulse is indeed equal to 50 kilogram meters per second. So our change in momentum is simply equal to mv minus mv original. And again, this is the same thing as impulse. We should get the same answer that we got down there. So I know all three of these. I know this mass is going to be 0.5. This mass is 0.5. I know the original velocity is -5. So if I can just find this final velocity, then I can find out what my change in momentum is. And hopefully that ends up being equal to 50. So we got to figure out what that final velocity is equal to. So I'm going to use one of these two equations. Any thoughts on which of these two I should start with? Top or bottom? Top one, absolutely. Because this bottom one is useful. It solves for final velocity. But we don't know what my change in distance is. So this is kind of invalid here. It doesn't get us anywhere. So we're going to use this top equation. And hopefully that's going to take us to our solution. Our goal, again, is to find our final velocity. So let's see if that gets us there. Now my original velocity is -5. My time is 0.1 seconds. I don't know my acceleration though. We were so close. So now we got to find acceleration. And hopefully if we can get acceleration, we can get velocity, which means we can get our change in momentum. So let's see if we can find acceleration. Hey, there's a couple equations with acceleration up here. By a couple, I mean all of them. If I'm looking for one that can be the most useful, I would point out this one. Because we know the force, it's 500. We know the mass, 0.5. So using this equation by itself, we should be able to get that acceleration directly. So using this equation right here, the acceleration is going to be equal to force over mass, just rewriting it. And again, my force is 500, my mass is 0.5, so I should have an acceleration of 1,000 meters per second squared. So now I can finish up this equation. So then we've got 1,000 times 0.1, so that's going to be 100. And -5 plus 100, I believe, is 95. And that then is our final velocity. So again, you know, not everything is completely a one-step process here. We had to really do a couple steps just to get this final velocity. And we're not even done yet. Because now we got to get that change in momentum. And can somebody plug this into a calculator for me, please? What's that? 50! Exactly! And that's exactly what we were hoping for. Because both of these things are solving for change in momentum. Whether you're using this method or whether you're using that method, you should get the same answer both ways, and we do, which means we should all have a big smile on our faces. Questions on this? Okay. This next one won't be quite as long, I promise. But it's another one where I'd like you to try and help me out with it and try and solve for it yourself before we go through. All right, so here's our setup. This fella has a ball, and he drops that ball from a height of 3 meters off the ground. And that ball goes down, and it hits the ground, but this is no regular ball. This is an awesome bouncy ball. So it doesn't just impact and stay in the ground, it's going to ricochet and bounce right back up. And it's actually, for the purpose of this section now, we'll say it is a absolutely perfect bouncy ball. We'll say it does not lose any energy into the ground on impact. So what that means is that if this ball is going down and maybe it impacts at, say, negative 10 meters per second, that means when it bounces back up, it's going to bounce up at 10 meters per second. And it would come back to the same height that it was released from. We actually call that a perfectly elastic collision. We'll talk more about that when we take some more notes later on. But yeah, so all I'm going to tell you here, and that's kind of the hint, is that whatever velocity this object has right before it impacts is the same velocity it's going to have when it bounces back up. So what I'd like you to try and find is the change in momentum. In other words, I'm asking you to try and solve for the impulse here. What is the change in momentum from right before the object hits the ground when it's moving at its fastest to the point in time right after when it starts moving back up? Okay? So you can kind of see what you have to do here. You have to solve for the final velocity right before it hits the ground. And then because this is a perfect collision with no energy lost, whatever that velocity is going down is going to be equal to whatever that same velocity would be going back up. And you're going to need to use those two velocity values to calculate your change in momentum. Well, that's the other little wrinkle. I give you the force of gravity, but I don't give you the mass. See if you can remember how to get the mass using this information. Go. I'll give you 3 minutes on this one, and we'll tackle it together.
So that's the force of gravity.
Yes. But you can get mass from the force of gravity.
Are we right? That was way too
You think you got the answer?
So mass? We were trying to figure out the mass.
Oh, okay. Okay, that's fine. Yeah. That's how you get your mass, yeah.
I kind of remember. We did go on
All right, so let's take a look at this together. So, as mentioned, we're given the force of gravity, but that is not equal to the mass. And if we're going to do this, we need mass, first and foremost. So, if I have my force of gravity, what do I got to do to it in order to get the mass? 9.8. That is the magic number. So, remember, force is equal to mass times acceleration. So that means mass is equal to force divided by acceleration. So we have the force of gravity, 0.7, and because it's in free fall, the acceleration is 9.8. So our mass is just going to be 0.7 divided by 9.8. So 0.7 divided by 9.8 is going to be equal to 0.0714. And that's in kilograms, of course. 0.0714 is our mass. We're going to need that if we're going to get our change in momentum. So, you know, there's two ways to get change in momentum, force times time, or mv minus mv original. Now, we don't have any information about force when it hits the ground, or time that it's impacting the ground. So, F times T does not help us here. So we're going to be going straight to this guy. And we've got half of the information. We know the mass. So if we can find how fast this object is going right before it hits the ground, then we can have the other piece of the information, the velocity. So if I want to figure out how fast this object is moving immediately before impact, I'm looking over here, and the one that really jumps out to me is this guy, because we're not given any information about time. We don't know how long this object is going to be in the air. You could figure it out because you have the height, but this is a one-way ticket here. You don't have to do a 2- or 3-step process to get velocity if you're using this equation. Now, I want to solve for that velocity. My original velocity is going to be 0. It's just released from rest. And then we've got 2. Acceleration is going to be negative 9.8. And it is descending 3 meters. It's going down 3 meters. So that's negative 3. And of course, because this is squared, we have to take the square root. And once you do that, you're going to find out that your velocity is going to be equal to 7.67. Now this is how fast you're going immediately before impact. And so again, because we have a square root here, we have the freedom to either add a negative or to leave it positive. We're going to add a negative here because if we're going down, that's a negative velocity. So if that's our negative velocity right before impact, that means this number is going to go right there. That is the original velocity right before it impacts the ground. So that also means then, because it's going to ricochet up perfectly and maintain all of its energy, that means this velocity is going to be positive 7.67. So now we have all of our numbers here. The mass is 0.0714. That goes there and there. And we've got our other numbers in. So let's see what happens. All right, so I'm getting about 1.1. And that would be my change in momentum here. In other words, that would be my impulse. So all we're doing then is plugging in the numbers into that equation, and that's all there is to it. So, just 1 second, folks.